Okay, so PS8 is out, due tomorrow, Friday. Some of you may have noticed that did the assignment early. So PS8C, that's where you submit your test cases for your C4 board. I changed it yesterday. So what I discovered was that no one who had submitted had been able to pass tests 3 and 8. There were a lot of scores where everything was passed except 3 or 8. And I was just too tired to figure out if I'd made a mistake or if it was just too hard, so I just got rid of tests 3 and 8. And made the other tests worth more to compensate. So if you saw your score go up, that's why. Any questions or problems about PS8 or anything else? Yeah. How do you, okay, so how do you debug recursion methods?
Yeah.
Okay, so that's an interesting question. What do you see as different about debugging a recursive method than a non-recursive one?
I guess it's hard to figure out on which stage of the recursion things went wrong.
Okay, so when you're debugging a recursive method, maybe we can look at it later today. One problem that occurs, if you set a breakpoint in a recursive method and the recursion goes 10 levels deep, it's going to hit that breakpoint, depending on where it is. It could hit the breakpoint all the way down. And that can be confusing to figure out what's going wrong. But typically, the problem is either going to be in the recursive case or the base case. And I don't have a good answer for it. I'll try to make a bug and we can try to debug it later. Any other questions? All right, before we start talking about recursion, I want to say a little bit more about PS8. In particular, I've had a number of questions from students about how to go about writing test cases for Connect 4 board. One question, it's an important question that showed up on Piazza today, was a student wanted to know if they could add methods or add a method to their class that would allow them to configure the 2D array inside the object, inside the C4 board object, to any state desired. So in other words, let's say they wanted to test if their code detected a tie correctly. They thought it would be handy to be able to just have a method where they could pass in a 2D array that had pieces in all the right spots. And that method would set the internal board to that state, and then they could do a test against it. And I had to say, no, you can't do that. Why? Why would it be a bad idea to add a new method to make it easier for you to do testing? Yeah?
Would it be grade scope that would have issues with it?
Okay, so would it be grade scope that have issues with it? And that's one way of putting it. Essentially, you're writing test cases to test not just your code, but my code. So if you start inventing methods, if your test cases depend on methods that only exist in your code, then it's not going to work against my code, because my implementation of C4 board is not going to have that method. So that's one reason. Another reason is, you're supposed to be testing a particular class, and adding a method just for testing purposes, just to be able to set up tests, is sort of defeats the purpose, because it changes the test. It changes the class. So how do you test to make sure that your C4 board detects ties, let's say, if you're not allowed to directly go manipulate the internal array into a tie configuration? Or how do you test for anything? So what's the secret? Suppose I want to test just that when you create a C4 board, all the squares are unoccupied. That's a basic kind of test, that at the initial state of a C4 board, there are no pieces on the board. There are no wins, there are no ties, there are no losses reported. There are no wins or no ties reported. How do you do that? Yeah?
Use the move to method multiple times
Okay. So that's not, I don't think that answers the question I asked, but if you wanted to test whether it was a tie or not, what you'd have to do is create a C4 board, make a bunch of moves, simulate a game with the move to method, and then once you've got everything set up the way you want, then make the assertion that it's a tie position. But what about for just testing that every cell is empty on a newly created board? Yeah?
You use the get occupant method to like check each square in the board to see if
Right, so we'd use the get occupant method, but first we got to create a C4 board. And one thing to realize is, yeah, the game itself uses a 7x6 board, but we don't have to make them that big. I'm going to make one 5x5 just to show you that I can. Okay, so I create an empty board, and now I've got to assert that every square is empty. So that means I've got to do something like this. So a doubly nested loop to generate all possible row and column numbers, all pairs of row and column numbers, and then I just make an assertion. I say assert equals get occupant, and I pass in I and j. Okay, so I just write a loop that makes an assertion about every single square on the board to make sure that when you call get occupant, it should return, I'm just going to make sure here, and it returns 0 if the square is unoccupied. Okay? How would you, suppose you in addition, you want to make sure that if that the board knows, you know, if you ask the board how many ties are there, it'll say 0. How would you make that assertion? Yeah.
Could you create another like doubly nested loop and then insert equals?
Okay, so the proposal is to create another doubly nested loop with an assertion in it, but we don't need to. We just have to make an assertion about B directly. So let's see, B dot get ties. How can we make sure? We'd expect if we call B dot get ties at this point, it's going to return 0, right? Because no moves have been made, and no games have been played. So how would you assert that it's doing the right thing? Ominous silence. Yeah, you just say you assert that that is equal to you do that, and it should be player 1's turn to move, right? So let's see, there's a method that says get to move, so we can assert equals something to b dot get to move. Okay, so we want to assert that it's P1's turn to move. So what should we put here? What should get to move return? Let's see what it says. It says returns P1 if it's player 1's turn to move, P2 if it's player 2's turn to move, or 0 if it's no one's turn to move because the game is over. Okay, so what should I put right here in front of that comma? Yeah, we assert that it's P1. Now the problem is it's going to tell you I don't know what P1 is. So how do I fix that? Right, it's defined in the C board class as a static constant, so we can just do C4 board.P1. So that's just basically that test is checking that when you create a new board, that first of all, every square is empty. Second of all, that if you ask it how many ties there are, it will say 0, and third, it will tell you that it's P1's turn to move. Yeah?
Can we not say assert equals 1, comma B to get
Well,
move?
okay, so he's saying, suppose I do that instead. That'll work because P1 is defined to be 1 in the class, but why is that slightly less desirable than doing it that way. Yeah?
Is it because one's kind of ambiguous and anyone who comes in and reads the code doesn't know what that one means?
Okay, so one reason is someone might read it and say, what's the one for? And saying P1 is more explicit. There's another reason, though. Makes the test more robust. Why would the test be more robust using the symbolic name c4board.p1 as opposed to the number one? Yeah.
If you were to change in the class, if you wanted to make P1 equal to 3 instead of 1, then it would still work.
Right, that's exactly right. If someone went back to the C4 board class and changed what P1 was defined to be, this would still test properly. But if we use the constant 1, we'd have to remember to go back and change that to a 3. Yeah?
But would you lose any points in grade scope if you did?
No, you wouldn't lose any points in grade scope, but just giving you general software engineering advice. Yeah. And if you don't like typing c4board.p1, you can do this. Let's see, it's called c4.c4board.star. That's an import static. And so what this says is import, basically it says make it so every static thing in the C4 board class can be referred to without qualification. So that's why once we do this up here, we can refer to P1 and P2 just as P1 and P2. We don't have to say C4 board.p1 once you do that import static. So that can make your code look a little cleaner sometimes. Any other questions? So it's kind of a pain to create a 7x6 board and fill in and make moves to make it a tie position. But just a hint, if you make it a 5x5 board, the code's a little bit shorter. So you don't have to stick with, you can make the board any size you want when you call a constructor. So take advantage of that. All right, now, we talked about recursion last time. We're going to talk about it some more today. So I want you to look at that method up there and explain to me why this method is correct. If you're trying to explain to another person that understands programming why this method does what it's supposed to do, what would you say? What's the argument that that method works properly? Public static, well, first of all, it's got a bug. Should say returns double there. So assume it says public static double for it. It's not a deep question. I'm not trying to trick anyone. Yeah.
So when you multiply exponents, or in this case, roots.
You say, okay, so you're saying that the square root of the square root is 4/3, or 1/2 times 1/2 is a quarter. Okay, so that's essentially it. You say, okay, we take x, we take the square root, we take the square root again, and we know from math that that's a 4/3, and we return it. Now, what I want to point out, what I just did, I didn't try to understand or argue about how square root works. Right? I just took it on faith that square root does what it's supposed to do, that it computes a square root. I didn't have to look at the code of square root. I didn't have to worry about what happens when the square root is called, how complicated that might be, how many method calls might be made. I don't care. I just know that if I call square root and I give it a positive number, I'm going to get the square root back. Okay? And that's how you reason all the time about programs. You just assume the library methods are going to work right, and you use what the library methods are supposed to do to convince yourself that your code will work right. Okay? Now, here's some code that's supposed to compute factorial. Now, I wasn't very good at putting return types in. This should be return static. It should say public static int f. Okay? And it says it returns n factorial as long as n is greater than or equal to 0. So it says if n is 0, return 1. That's the right answer when n is 1. Otherwise, it returns n times math.factorial of n minus 1. So let's imagine there's a factorial method in the math class in Java. Okay? So someone explain to me why this works. Sort of make the same argument that I did when I was talking about this, the fourth root method. Yeah?
Because n factorial is equivalent to n times n minus 1 factorial.
Okay. Because we know that n factorial, this is the mathematical fact, that n factorial is equal to n times n minus 1 factorial. And obviously, if math.factorial does what it's supposed to do, that will compute n minus 1 factorial. And then we will multiply that by n and get n factorial and return it. And we wouldn't argue or worry about what that method does when we call it. We just assume, okay, whatever it does, it computes the factorial of n minus 1 and returns it to us. And we wouldn't lose any sleep over that. We just accept it and move on. So we base our assessment of whether or not that method is correct on the specification of this method. We don't peek at the implementation. We just worry about the specification of that method factorial. Just like we depended on the specification, not the implementation of that math.square root method. Okay? And this is something you do all the time when you write programs. So, here's a different version. I replace math.factorial with a recursive call to f. Now, someone explain why this is correct. Yeah?
Because it says in the Java doc that f is n factorial.
Yeah. It's the same argument as the last example. Let's look down here, where we know that n minus 1 factorial times n gives us n factorial. And what we're doing is, well, we're calling f on n minus 1. Well, what does f do? It computes the factorial of its parameter. So, we just take it on faith, just like when we called factorial, the imaginary factorial method or the square method, that this is going to do what it says it does. We get n minus 1 factorial, multiply by n, and return it. We're done. This really works. This is how you reason about recursive methods. You assume that the recursive call is going to work as specified, and if you can convince yourself, based on that assumption, if that allows you to convince yourself that your method is correct, then it is correct. You don't have to waste brain cycles, thinking about, okay, this calls f, that calls f, that calls f. Don't worry about that. Just when you see that call to f, just treat it like any other call to any library method. Just assume that it works as specified up there, and then try to use that fact to convince yourself that this code works as specified. You're just going to have to trust me that it works. Now, you got to be a little bit careful. So what do you think of that method? What would happen if you applied what I just said? So what I said was a little bit misleading. You could also argue this is correct, right? What would the argument look like?
The argument for it being correct.
Yeah.
Well, we trust that f returns n factorial.
Right.
We just return n
So we're making a recursive call, and we say, okay, I'll assume it does what it says it does, which is computing n factorial, and so we compute it and return it. And then we're doing the right thing. Okay? So, which slide is right? The last slide, this one, that factorial actually works. This one, what would happen if you called f? You get an infinite recursion. You know, you call f of 10, it'll just call f of 10, it'll call f of 10, and it's infinite recursion. What happens is a little bit of memory is added to the stack, each call to f. Eventually the stack will run out of space and you get a stack overflow exception. Okay? All right. So here's the real deal. What I was talking about 2 slides ago, what I've been talking about is what's called partial correctness. A method is partially correct if it's correct assuming that it ever terminates, that it ever returns. All right? That's what partial correctness is. So, is that method partially correct? If it returns, will it return n factorial? Yeah. Is this one partially correct? Okay, I've got some yeses and some nos. So let's be clear. The argument you have to make is if this method returns, it will return n factorial. Okay? Does it return n factorial every time it returns?
Does it return?
It never returns. So yeah, every time it returns n factorial. Okay? It never returns, so it's vacuously true. So that is partially correct as well. But we don't care about partial correctness usually. We care about total correctness. Total correct means it's partially correct and it always returns. So going back, we know that's partially correct. Is it totally correct? Yeah. It always returns. What's the argument that it's not going to go into some infinite recursion? Why do we know that it always eventually returns?
It'll go down to the base case, and the base case returns.
Why do you know it's going to go down to the base case eventually? I'll get your answer to that. Yeah.
Well, because it decrements by minus
Right.
1.
The point is, every time we call f recursively, it's with a smaller number. And that number eventually hits 0. And then that breaks the recursion. It stops the recursion. So that's usually you reason about partial correctness separately from reasoning about total correctness. What about this one here? We argue that it's partially correct. If it returns, it'll return n factorial. In fact, if it returns, it'll return the square root of n. It just never returns. But is it totally correct? No, because it doesn't always return. It never returns. So the way you reason about partial correctness is, so when we're reasoning about partial correctness, that's when you just argue, you have to convince yourself that the method returns n factorial, assuming that this recursive call returns n minus 1 factorial. That's the partial correctness argument. But then you've also got to argue that it will always terminate. That's an additional thing you have to argue. And the argument usually is in the form that every time you make a recursive call, the parameter gets simpler. And eventually it can't get any simpler, and that stops recursion. So that's that there. And why does that argument fail here? The argument that this always terminates. Is anything getting simpler? No, it's always the same parameter, so it's not getting simpler. Yeah?
When we did, what was it called, the pedigree chart, would the objects considered to be getting simpler?
When we did what?
The pedigree chart.
Okay. So in the pedigree chart, I'll answer that. We're about to look at that again. So I'll answer that when we get there. I'll ask you, if I don't remember, remind me. We'll see what's getting simpler in those recursive calls. But the whole trick to exploiting recursion is the willingness to treat this method right here, that's recursive, that makes that recursive call to f, treat it the same way with this one here, which is making a call to another method that computes n minus 1 factorial. It's the same reasoning you convince yourself it's correct. You just have to be willing to say, what you have to do is convince yourself the code is correct, assuming that the recursive call will behave as specified. That's the whole thing. You just have to have that faith. If you insist on understanding recursion by having to first understand what happens in memory when it runs, it's going to be a long time till you understand recursion, because you have a very weak understanding of what happens inside the computer when a program runs right now. But even with that weak understanding, you can write recursive methods. So let's look at what you did. You looked at this in lab yesterday. I want to look at it some more today. Here is the pedigree tree. So that's sort of one in its full glory. We've got some number of people, 8 people, connected depending on who fathers and mothers are. So we talked about that last time. And we did this last time as well. I said, let's let a triangle stand for an arbitrary pedigree. Okay? So there are only 2 kinds of pedigrees then. Null is an empty pedigree. So if you don't know anything at all about your mother or your father or some ancestor, then we just represent them with null. We don't know anything about them. And the other kind is a non-empty pedigree. It's going to be an object that contains a name, a year, a father and a mother. And father and mother are references to other pedigree trees. Those other pedigree trees could be null or they could be non-empty. What's the advantage of being able to say that any pedigree tree fits one of these two forms? Why is that better? Why is it better to think of a pedigree tree? It's hard to think about how you'd write a method to count all the people in that pedigree tree. It's easier to think about counting all the people in that pedigree tree. See, the important thing is, rather than there being an infinite number of different pedigree trees, which makes it very puzzling to figure out how to write methods to cope with that, you realize there are only two kinds of pedigree trees. So when you write a method, you've got to cope with null pedigree trees, and you got to deal with the other kind of pedigree tree. And that's all. So how do you compute the size of that pedigree tree right there? By size, I mean the number of people, number of people named in the tree. Yeah?
Having the size of the mother tree and the father tree.
Right. You recursively calculate the size of the father tree, and you recursively calculate the size of the mother tree, and then you add them together and add 1, and that gives you the size of the whole thing. Okay? So we'll see that in action. So here's a pedigree tree again. So look at Wayne there. So rather than view Wayne as in that form, I'm going to view it in this form, where in this case, both of the triangles happen to stand for nulls. So this turns out, because there are only two kinds of pedigree trees, then the code that consumes a pedigree tree is always going to have that shape. There's going to be a base case that occurs when the pedigree tree is null, and there's going to be a recursive case that occurs when the pedigree tree is the other kind. And then in the recursive case, what you're going to do is recursively deal with p.getMother. So you recursively do something with the mother pedigree tree, you recursively do something with the father pedigree tree, and then you take those answers and combine them in some way to get the overall answer. It's always in that form. So when you go to write a method, you can start by copying the previous method. It's going to be the same if-else form. Let's go see that in action here. Pedigree tree. Okay, so first of all, I want to make sure you at least have seen this code. So I created a class called Pedigree. A pedigree object contains within it 4 instance variables: a name, a year, a reference to a father tree, and a reference to a mother tree. So that's just like those diagrams I showed you. One of these objects is like one of those boxes. It contains the 4 things: a string, an int, and 2 pedigree references. The constructor is very simple. It just takes the 4 things in and assigns them the instance variables. So that's very simple. And then you can get the name, you can get the birth year, you can get the father, you can get the mother. So that's about as simple as a class gets. A constructor and some getters. Okay? Much simpler than, say, a C4 board. Any questions about this? This is how you build these pedigree trees so you can operate on them. All right, now we'll look at pedigree demo. So pedigree demo has a main method. So first thing it does is it creates a pedigree tree by calling a make pedigree method, which is right here. So look at that, and you'll see there are 8 variables declared, 1 for each box in the diagram. And you'll see that I start with the older ancestors, like James and Larry, and work my way down to Ben, who's the youngest. Why do I do it in that order? After all, Ben is at the root. It seems like I would create the root first. Yeah?
Because you can set the fathers and mothers for each one up.
Right. I can't create Ben until I have I have Sam and Jane created. And I can't create Sam until I have Larry and Chris created. So I work from the leaves of the tree to the root. in the end I return bin. So that builds a structure just like those diagrams I was showing you in the computer's memory, where the arrows in the diagram are references, Java references to other objects. So here is the size method that I gave you for the lab. Notice that it has that structure I told you about on the last slide. It has the base case, which occurs when p is null, and it has the recursive case, which makes a recursive call to, with the father tree, a recursive call with the mother tree, and then adds those two together and adds 1 and returns it to get the overall size of the tree. So the question you have to ask, how would you convince yourself this is correct without testing it? It's a simple method. It just makes a couple of other method calls, not much to it. How do you convince yourself it's correct? So apply the reasoning for partial correctness that we applied to the factorial method.
It returns something.
What's that?
It returns something.
Well, it returns something, yeah. But what assumptions are we going to make? What's the assumption we make when we work on it? Yeah.
That size will always get the size.
Right. We assume that size, that when we call size on the father pedigree tree, we will get back the size of the father pedigree tree. And the same thing for mother. And then you just have to convince yourself that if you know the number of people in the father tree and the number of people in the mother tree, then the number of people in the whole tree is just going to be those two numbers plus 1. Where's the plus 1 come from? The person itself at the root. So the 1 is for bin, if we're initially calling size on bin. Bin is the 1. Then we get the size of the father tree, the size of the mother tree, add them together. And you just have to assume that size is going to do what it says up there. So that's partial correctness. How do you argue that it's totally correct? How do you argue that if you feed it a pedigree tree, it will eventually return as opposed to running forever? In other words, what's getting simpler? There are no numbers here that are getting smaller. What's getting simpler? Yeah?
Less information you have, just as it goes on, there's less branches.
Okay. So every time you call with a pedigree tree, the two subsequent calls are going to be for smaller trees, right? Because the initial pedigree tree contained these two subtrees. Now we're taking the subtrees in isolation and making recursive calls, so they're smaller than original. So every call is to a smaller pedigree tree. And what bottoms out the recursion? Yeah?
Eventually that you're going to get to a null pedigree tree.
Right. Eventually you get down to the bottom where the father and mother are unknown. They're just null. And so we hit the base case and we terminate. So that's sort of null as the simplest kind of pedigree tree. Okay? So you don't have to go dizzy trying to visualize what happens as the method takes the trees apart. I've tried to do that in class before, set breakpoints and try to illustrate what's going on, and I've never succeeded at it. It's just too much to keep straight in your head. It's much easier to do this reasoning method that I was telling you about. Just assume that the recursive calls work as specified up above, and then reason from there. All right, now I know you did this in lab yesterday, but I wager a lot of you don't remember or didn't do it, didn't get it done. So what I want is 0 if p is null. Otherwise, I want the depth of p, which is basically the number of generations in the longest branch. So if we go back to this picture here, what would be the depth of that pedigree tree? 4. The longest branch is the one on the left. There are 4 people on the longest branch. Longest chain of ancestors is 4. And we'll call a null pedigree tree, we'll just say its depth is 0. So what would be the depth of the pedigree tree if we just looked at Jane here? What's the depth of that one? 2. Either this branch here or this branch there. And for Sam, it's 3. For Chris, if you just look at the Chris tree, it's 1. So I want a method to compute that. So what I say we do, I told you the structure, they're all going to have the same structure. So I'll copy that and paste it here. And we just we know, in fact, we know we're going to need to make a recursive call here. wait, it's going to be depth. We're going to recursively have to compute the depth of the father tree. And we're going to have to recursively calculate the depth of the mother tree, and we got to return something up here as in the base case. Right? So there's our starting point. You know that's the structure. Even it doesn't even matter what the method does. If you know that it consumes a pedigree tree, it's going to have that structure. All right, base case is usually easy. And in this case, it's easy because it says up there what the answer is if p is null. It says 0. So if p is null, we better return 0 or the method won't be correct. Okay? Now, if you knew the depth of the father and you knew the depth of the mother, what would be the depth of the overall tree? Okay? Let's get one on, yeah.
The depth would be whatever the larger depth of the father or the mother.
Okay, so we figure out the depth of the father and the mother, and we take the larger of the two. Okay, and we can do that with math.max. So we take that, comma that. All right, and continue. What do we do then?
Then add 1.
Okay, then we add 1. So if we go back to the picture here, if we're trying to calculate the depth of Ben, we figure out the depth of Sam, which we said was 3. We compute the depth of Jane, which is 2. 3 is bigger, so we take the 3 and add 1, and that gives us that depth of 4. So back to here. There's our answer. We just return it. So where in all of this was there any creativity required? What was that?
Finding out which depth to use from the father.
He said figuring out which depth to use. I would put it a different way. Yeah, it does have to do with the depth there. And maybe I wouldn't put it a different way. But anyone else want to say? Mm-hmm.
More like knowing how to use depth to your advantage.
Okay, he said knowing how to use depth to your advantage. So putting those two together, I would say the creative part is always taking the results of the recursive call and figuring out how to combine them in some way to an overall answer. That's the creative part. You know you're going to have that if-else structure. The base case is usually trivial. You know you're going to have to make recursive calls on the father and the mother. So all that's left is to figure out, okay, what I have to do with the results of the recursive calls is take the max of the two and add 1. That's the programming part, if you will. The rest you can almost do without thinking. All right? What about this next one here? Now, you did that in the lab too. I'm going to skip over that one. What about this one here? Print names. I want to print the names of all the people, 1 per line. All right? Take a couple minutes and start working on it. Talk to the people around you. Remember, the first step, you know it's going to have the same. I think you can remember that you're supposed to print out all the names, so I'll put this slide up. You know, if you call it on this tree right here, it should print out Ben, Sam, Jane, Larry, and so on in some order. I don't care what order it prints. You know that it will have structure just like size and depth. You got a question? Okay, let's see what you come up with. So let's follow my advice. I'm going to copy this method here. I'm going to put it in here. And I've got to do something in that case. And I've got to do something down here. I don't know what it is yet, but I know I'm going to have to call print names recursively. And I've got to call over here print names recursively. And then I've got to figure out, at that point, all I've got left is to figure out, do the creative part. So let's start with the base case. What should we do in the case when P is null? I heard return. Is that right? Do I print something? Yeah, the thing is, it's a void method, so there's nothing to return. We either print something or we don't. So that's an easy decision. There's nothing you can print for null. That doesn't have a name. So, oops. So we just do nothing if it's null. What do we do if it's not null? What do you do? What do you have to do besides call print names on p.getFather and print names on p.getMother? Yeah. Yes. Yeah. So this is going to print out the names of the father, the names of the mother. All that's left is to what is it? Name p dot get name. Okay, so we print the father, the mother, the get name, and people will look at this and go, that can't possibly work because there's only one call to print line. What if there are 100 people in the tree? How will this print out more than one name? And what's the answer to that? Yeah?
There are 100 calls in the print line because every time that it goes and recursively calls itself on father and mother, it'll hit the print line.
It's going to get called once for each person. It's the same thing. What I just said is the same. You might look at a loop and have a print line inside a loop and say, there's only one print line in this loop. How is more than one thing printed? It's called the loop goes around. That one print line, it appears right there only once, but it's called a number of times. Now, let's print it out. Let's run it. Somewhere in there is going to be the result. So here are the names. James, Larry, Chris, Sam, Wayne, Maud, Ben. Now, why did they come out in that order? Let's see, we do James, Larry, Chris, Sam first. So if we go to the picture here, James, Larry, Chris, Sam. So it sort of worked from the leaves back up. And then it did, in some order, Wayne, Maud, and Jane. And it ended with Ben. So why did it go from the leaves up? Yeah?
So because you're calling print names p.getFather first.
Okay, we printed out the father side first, and then the mother side. What if we wanted to print out the mother side, the names on the mother side to come out before the names on the father side? What would we change? Right, if we just did this, that would print out the mother side names for the father side names. What would happen if we made this change? So it printed out p.name and then the mother side and then the father side. In what order would they be printed now? What would come out first? Ben. So it would print them out sort of top down now. So if I do it that way, you'll see it went from the younger generation to the older generation. So a lot of you are going to be taking 24/20 next semester. And at some point, Professor Parker is going to ask you, have you ever seen a binary tree? Okay? And I want you to know right now the answer is yes. We've been calling these pedigree trees, but a pedigree tree is a kind of binary tree. What makes it binary is that we've got we have elements in the tree, and they have at most 2 children. In this case, they have exactly 2 children because of the way we handle nulls. if we count the nulls as being children. So this is the shape of a binary tree. You'll be studying things like pre-order traversal and post-order traversal and in-order traversal and reverse in-order traversal. And I'm just going to tell you now, I'm not going to define those terms, but that just refers to when you consume a binary tree, you're going to consume the current node in some, at some point. You're going to deal with the right subtree at some point, and you're going to deal with the left subtree at some point. And the order in which you do those determines what kind of traversal it is. So this is actually a reverse pre-order traversal, meaning we start from the top, but we go right before we go left. So pre-order means start from the top. Reverse order means we do the right subtree before the left subtree. So I'm not going to ask this on any tests. I'll never talk about it again. But I'm just hoping that sometime in January or February, when you hear this again, you'll think back on this example and realize, yes, you've seen binary trees before. Okay? Let's take a break. Here's another picture for you. This is meant to represent a piece of a file system on a computer. And the shapes I'm using, this sort of file folder looking thing is a folder. So it stands for a folder on your computer. And you can think of this circular oval thing as a document. And then I'm going to use triangles. There are no triangles in the diagram above, but I'm going to use them to stand for either. So a triangle can either be a folder or a document. That's what Java calls a file. This is going to be a bit confusing because Java doesn't use terminology like folder and document. It talks about files and directories. Anyway, file, and furthermore, a file can be either one. So anyway, I'll explain about the triangle later. So this shows you've got a docs folder. And the docs folder contains a CS1, a CS22, and a CS33 folder. The CS22 folder is empty. The CS1 folder contains another empty folder and a file, a.java, and so on. So that's a piece of a file system. Now, if you were going to write, what questions might you ask about a file system? All right, we've been asking questions about pedigree trees. What kind of questions might you ask about a file system? What might you want to calculate? Yeah.
Like how fast you can access a certain document or file.
Okay. Might be, he said, how fast can you access a certain file or directory? Okay, that's certainly something. I'm not prepared to do that example today, but yeah.
How many folders do or do not have the document inside them?
Okay, so how many empty folders are there, or how many non-empty folders are there in the entire tree? Okay, yeah.
Maybe the size of the folder itself has documents or doesn't have documents.
Okay, so the size of the folder, or maybe files, may be a better example. What's the size of the largest file in the whole tree? Or if we call the size of the folder to be the number of things it contains, which folder contains the most things? Or we could ask, what's the depth of the tree? What's the longest path in the tree, just like for the pedigree tree. So lots of things we could ask. Now, when we write methods to answer questions like that about pedigree, about file systems, what will be the structure of the methods? Will it involve loops, or will it involve recursion? Well, I'll let you hold on to that question for a second. So I claim there are only two kinds of things in this tree back here. Two kinds of files. That's what Java calls everything, a file. Okay? One kind of file is what we think of as a document. And the other kind of file is a folder that contains these triangle things. So what do these triangle things stand for? Not folders. They stand for either documents or folders. So that's what lets us think of, there are only two kinds of files. There's the kind that's a document, and that's just stands by itself. There's the kind that's a folder, and folders contain other folders or files. So this first triangle might be a file, a document. This other thing might be a folder. This other thing might be a folder. We don't know. It doesn't matter. Just like before, we were using triangles to stand for either null or a person. So there are two kinds of files, and this turns out to be the shape of a method that consumes a file, a file system, if you will, in Java. We got the base case, which is basically saying, okay, if f is a document, the names for the methods that Java uses are really confusing. But isFile will tell you whether it's a document. So if it's a document, that's the base case. And you answer the question directly about it. Otherwise, the recursive case, you have to have a loop that looks at everything the folder contains. So f.listFiles will give you back an array of everything the folder contains. And then you have to make a recursive method call, a recursive call on each thing. So you have to have a loop that makes recursive calls. Now, why didn't we have loops that made recursive calls with the trees? The pedigree trees. I lost the word for that. Why didn't we have a loop in it? Yeah.
It was redundant.
Well, what was redundant about it?
You didn't need a loop because it was.
Okay. You didn't need a loop because there are only two. There's one mother and one father. It's always two. But with a folder, there could be 0 things in the folder. There could be 100 things in the folder. So we need to deal with each one in a loop. And so there's the pattern we're going to see. So the theme we're seeing here is that very often, or always really, recursively defined data structures are consumed by recursive methods. So the pedigree tree was recursive because a pedigree tree contains simpler pedigree trees. And similarly, a file system contains simpler file systems. So in both cases, we have a recursively defined data structure that needs to be processed by a recursive method. And for each kind of structure, the shape of the recursive method is going to be the same. So let's try to write such a method. Where I got to go now is file system demo. So notice I'm using actually the data on my computer here. So I'm creating a method called count files. And we give it a file which represents a folder on my computer. And it's supposed to count how many files are, how many real files, how many documents are contained inside. So here's that method. It says if f is a file, returns 1. Otherwise, returns a number of files, not including directories, which are folders, that are contained directly or indirectly inside of f. So it's counting documents, to use more familiar terminology. And I'm just going to take a minute and type in the shape. So it was if f.isFile. So you can squint at that and imagine that says is document. So we do something if it's a document. Else, now what I said we had to do is we had to grab everything contained in the folder. So if we get to the else clause, we know f is a folder. So we iterate through everything the folder contains, and we have to make a recursive call to G and do something with it. So that's the rough shape of the method. So once you know that, it's just a matter of filling in the pieces. So let's work through this. If what we've got, so the thing to remember is this means that we're dealing with a document. And this else means we're dealing with a folder. And G down here can be either, we don't know what G is, it's either a file or a folder. Either a document or a folder. Just down. So what should we return if F is a document? Look at the comment and tell me. In fact, let me just change the comment, put this in more. So if F is a document, returns 1. Otherwise, returns the number of documents that are contained directly, indirectly inside of the folder F. Okay. So if I'm in my documents folder on my computer, I want to know everything in that, every document in that folder, and every document in the folders that it contains, and so on, all the way down to the bottom. So what should I return? What is the size of, what should we return if F is a document? 1. That's the first sentence in the, okay. All right. Now what do we do? I'm going to put this up here and get it out of the way. G is document or folder. All right. Now we've got to somehow count up all the documents. So when we call count files of G, where G is some piece of the file system, what's it going to return? What will that do for us? Let's go back to the picture. So we're trying to count all the documents contained in this folder, directly or indirectly. What will we get back when we call count, when we do that count for this piece of the file system? What number do we get back as the answer? Counting documents. 1. There's only 1 document. So we'll get 1 back for this recursive call. How many do we get back for this recursive call? 0. And what do we get for this recursive call? 3. So you got 1, 0, 3. What do you do with those numbers? You add them up, and that's your answer. So basically, you just count how many documents are in each of the subfolders, add them up. So let's do that. How do we get this to add up all the results of calling count files of G? What kind of loop do we need? Yeah, accumulation loop. I'll call this count. So we're going to create a count. It starts at 0. When we're all done, we're going to return it. And what do we put here? Yeah. We just add them into count. And that's all there is to it. Now, people look at this and they're going to say, can't possibly work because, after all, the base case only returns 1. I hear that a lot. It's going to keep making recursive calls until it hits the base case, and the base case returns 1. So shouldn't this method return 1 every time it's called? And that thinking, I think when students think that, they're thinking that, okay, I know when it returns 1, that's the end of the method. And so they think, okay, when it hits that return 1, the method is over, the answer is 1. But what's wrong about that, making that analogy? Back there. Yeah, you. Yeah.
Okay, it returns 1 to each of the recursive calls, and so then it passes that parameter up to the original call.
Right. So way down, as we're doing our computing, down on the leaves, when we count the documents, yeah, we return 1. But there's another return statement right here that returns count. So it's taking all the ones that are returned by these recursive calls to count files and adding them together, getting something bigger, and returning that. So the return, yes, the return ends the current call of the method. But if the method calls the method, calls the method, calls the method, and we're 4 levels deep, and this method returns, it doesn't wipe out everything on the stack. It just wipes out the current call. Then the most, the invocation of the method that was most recently made, that made the most recent call, takes over. So don't think of a return as it's all over, main now gets control back. No, it takes a while for that to happen. Let's run this and see what's going on. So I have to make this bigger so you can see. So it counted and found out that in my, it's just a folder I have for this class on my computer, 3,814 documents are contained in there. Now, let's instrument it. Let's say every time before it returns, let's have it print out. Why is that not working? What it's returning. So we'll have it print out 1 right there, and we'll have it print out count right here before it returns. So this might be one way. I remember you asked me in a class how to debug. This might be one technique. Let's see if it works or not. There's probably going to be too much information. What is going to be printed out? What are we going to see down here when we run this method? How many lines of output will there be? Will there be 3,814 lines? Will there be more? Will there be less? I've heard of less. I heard of more. Anyone think it's exactly 3,814? Yeah?
For every single count, or bit of count, every 300, whatever, 2,000, there are 2 system outlines because it has to go to the system out at F is file the base case, which we get a number from, and then when it's added to something.
Okay. So let's look at this tree. Suppose I called that method on this thing here. How many lines of output would it print? Well, first of all, is it true that every time you call the method, it prints a line? Let's go back and look at it. If you call this method, it's either going to execute that print or it's going to execute that print, but not both. So every invocation of the method prints out 1 line. How many times will the method be invoked? On this one right here. We call it on docs, right? That's 1. Then we call it on CS1, that's another. It'll call it on P1, that's another. A.Java, that's another. So at that point, when we're all done, how many method calls would have been made? 1 per what? Yeah, 1 per node in the tree. 1 per folder or document. So in this case, it would print out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So I'm going to get more than 3,814 lines of output. Those are just, there'll be 300, what will be printed 3,814 times? the number 1 will be printed out that many times, because that's printed out every time we hit the base case, which is a document. Bigger numbers we print out for each folder. So let's run it and see. Let me bring this up. I don't know why there's 308. The count went up. How could that happen? No, I'm using Eclipse. It must have created a file. All right, so we got all that stuff printed, and the very last thing that got printed was this here, 3,815, because that's the last thing that the top level method prints out, is what it's returning. Okay, so you can see there's a lot going on with just a little bit of code. And it's truncated, so you don't even see all of it. All right, let's stare at that a little bit longer and see if you have any questions about it. I realize I'm combining recursion with the loop, but I'm just assuming that you're comfortable enough with an accumulation loop right now that that's no big deal. Yeah.
So what would be an instance where you'd use like recursion for like other types of loops, like recursion or system or searching?
Okay. He's asking when might we have things other than accumulation loops? Okay. So for example, suppose we wanted to find the largest document in a file system. That would be an optimization loop. Or we want to find a Java file. That would be a searching loop. Okay. I think you had a question over here.
Yeah, so the first time you ran it, you got the total count. Was it giving you the count plus the base on top of that, the base case? Or is it an either or?
It's either or. Either if it's a document, the answer is always going to be 1. If it's a folder, the answer is going to be whatever.
Okay.
Depends how many, what it contains.
So the 3,814 came from the else.
Yes. Other questions? I'm going to comment these out. And we're going to look at another one. If f is a document, returns its size. Otherwise, it returns the size of the largest document that is contained directly or indirectly inside of folder F. If F contains no documents, return -1. So if you were confronted with the necessity to implement this method, and you had to write some code, where would you start? Just like there are patterns in loops, there are patterns in recursive methods. Well, there's the base case, there's a recursive case, but how can you get some code for free? We already wrote the method with that pattern, so let's just copy this. It's going to have the same structure. We're going to paste it there, and let's see what we got to change. So I'll get rid of that. And I'm not sure what we return here, so I'm just going to say return 0. And down here, we're going to have to, I don't know if we need that. We don't need that. We're going to return, so let's just clean it up and get stuff we're sure we're going to have to do. We're not going to recursively call count files. We're going to call largest file size. Okay? So there's our strategy. If it's a document, we got to do something special for documents. Otherwise, we got to loop through all the files and make a recursive call and calculate what it is we're going to return. Okay? So far, no real thought required. I just put it. It's like deciding something's an accumulation loop and starting with a pattern for your accumulation loop. So we start with the pattern. All right, it says if f is a document, returns its size. So that tells us what to do in the base case. So how do we figure out the size of f if we know it's a document? Well, what would you do if you had to figure out this? You had a file object and you had to figure out its size. Yeah, you'd look for a method. So you go f dot, and it turns out there's a method called length. Now, it returns a long because files can be bigger than 2 billion bytes. So you notice that I'm returning a long as well. So that's a case where long is absolutely required because files can be so big, documents can be so big. All right, so that takes care of the base case. And again, base case usually requires no thought, very little thought. Okay, now we're going to recursively calculate the largest document contained inside the folder F. So how are we going to find the largest overall document? In fact, I'm going to change this and call it doc, so we remember we're looking for doc sizes. What kind of loop are we doing? Yeah.
Oh, I was going to say we need to put a condition on there because now we're doing optimization.
All right, it's an optimization loop. So now it's a different pattern. So for an optimization loop, we first need an optimization the variable. So we'll have long, we'll call it largest. And it says up here, if there are no documents, I should return -1. So I'm going to start my variable there, and when we're all done, I'm going to return largest as the answer. So there's our standard accumulation loop. And we know that in here we're going to have an if, and if it's true, we're going to have to update the variable. And let me take this out of here, actually. So there's sort of our pattern. So what do we do with each thing G? Yeah?
Compare with largest.
Okay. So first, so let's do this. Long, largest doc size G. So if size is greater than largest, then something like that. Okay. So let's see, what we're doing is for every G, we're figuring out how big it is. And if that's bigger than the largest thing we've seen so far, we have a new champion. And when we're all done, we return largest. And as long as this recursive call does what it advertised, which is to return the size of the largest document in G, this whole thing ought to work right. Okay? Let's see if it does. Let's see what the largest document, the size largest document is. Oh. What did I do? Oh. Now I'll run it. Okay, so 4 megabyte. That's it. 40 megabytes. Okay? Almost like magic, but that's how you feel about recursion sometimes. It just seems like magic. All right? Let me show you something not to do. You might be tempted to do this instead. Let's copy that and just use it here. So if the largest doc size of G is greater than largest, we do that. And let's see if that makes a difference. So let's make some room here and run. So first of all, you see what I did. I just, instead of calculating it once and saving it in a variable and then using the variable, I call it twice. Once for the comparison and once to update largest. Okay, so it figured out did the count pretty fast. Okay, we could be here until universe suffers a heat death, and this would not be finished. And the reason is, so at the top level of the file system, how many recursive calls are we making? Right, so for everything that the top level contains, we're making 2 recursive calls. And each of them is making 2 recursive calls. So that's really 4 recursive calls at that level. And then 8 recursive calls, and so on. And so if you keep doubling the number of recursive calls being made, the deeper in the tree you get, the number of recursive calls really explodes. And very quickly get a, I guess the universe didn't have a heap yet. But if the, because I got an answer. But if the file system was deep enough, this one's not very deep, but if it was like, say, 100 levels deep, it would take, literally would take forever. Well, not literally. It would outlast all of us. So you don't want to do what I did there. Just want to make that recursive call once. Making it twice can be a problem. Okay, so let's stare at this code and see if you have any questions about it. Yeah.
So I'm just curious, in the part where it does the optimization for the conditional, could we use something similar to like the top length for the to determine if it's
I mean, instead of making a recursive call, do something like g.length.
well, I guess instead of like creating a size, could we have actually just done like what you did up above where you just got the dot length?
No, if we did g.length would tell us if it's a folder. It doesn't tell you the size of everything it contains. It's just the size of the data structure that represents the folder.
Oh, okay.
All right. Let me tell you about PS9. So PS9 is going to involve recursion, as you might imagine. One of the things you'll be working on is methods that manipulate mobiles. So you know what mobiles are? They're like, there'll be something suspended from the ceiling, and it'll have a line that comes down, and then there's a rod, and then there's like weights hanging from it. And depending on, you can go arbitrary number of levels deep, right? And it sort of hangs there and is pretty. All right. What questions might you ask about a mobile? So I'm going to give you code to represent a mobile. What questions might you ask about it? Yeah. What's the depth of a mobile? That's true. Yeah. How many bobs are there? Okay. What else? Yeah?
Is the distance between the connection, is it always symmetrical?
Yeah, it's not always connected to the middle. So it could be suspended like, where the wire that comes from above doesn't go to the middle of the rod. So a question you end up asking is every rod level? Is the mobile balanced? The torques match. It's not going to spin. It's a two-dimensional thing. So first of all, why am I asking a question about mobiles if I'm interested in recursion? Yeah? It's a binary tree, basically, yeah. Okay? A mobile is either a bob, that's the base case, or it's like a rod that has two mobiles hanging from it. That's the recursive case. It's a binary tree. We'll represent it as a binary tree. And that means that all your methods are going to have the same structure, which is going to be very similar to the structure of the pedigree tree. In fact, it'll be identical. There'll be an if and an else, and the else makes two recursive calls, one for each side of the mobile. And the base case will be a rod, will be an individual bob. So students often make this assignment so much harder than it needs to be. Every method you're going to write is going to be basically the same structure, and it's going to be very simple. But people will write the most convoluted, complicated code you can imagine, and then you ought to see their jaw drop when they see the solution. It's like, how is this even possible to solve it with so little code? Okay? So the inspiration for writing the code is to look back at the first example today, Pedigree. Yeah.
How long do you think it should take us to write this?
I won't speculate how long it will take, but I will say that as a programmer for a long time, I know that sometimes I write code that's more complicated than I wish it were, and what I always say is I would have made the code briefer, but I didn't have time. Sometimes it's the first way you try it, it's too complicated. But if you stay at it, it can become very simple. So that's what's coming up. So see you next week.